Welcome to the next lecture of Switching Theory and Logic Design. In this video, we are going to discuss the topic of shift registers. In the last class, we have seen what is meant by a register and what is meant by buffer register and what is meant by controlled buffer register. These concepts we have seen in the previous lecture. Now, let us see the concept of shift register. A register is a device which is used for storage and where the shift register is used for shifting the data from one flip-flop to another flip-flop or some one location to another location. So mainly in this register we have two operations. One is storing and second one is shifting. Let us see what are the different types of shift registers are available. Right. Before that, see the definition of register. A register is capable of shifting the binary information held in each cell to its neighboring cell in a selected direction is called shift register. So shift register, see here we have different cells. So we are represented here with some orange color, dark orange color represented boxes. So this box is first flip-flop, this box is second flip-flop, third, fourth, 5, 6, 7, 8, 9. So like that here we have some flip-flop. So from one flip-flop to another flip-flop, the data is shifting. Okay, so here it is shifting towards left to right and this is shifting from right to left. Okay, so these are the two shift register. So here we are giving the data at left side, here we are giving the data at right side. Okay, so that means here we are shifting the data from left to right and right to left. Now let us see what are the different types of shift registers are available. So here shift registers, we have four different types of shift registers are available. The first one, serial input, serial output configuration, SISO configuration. So in this we are giving the data at left side and right side. Next, serial input, parallel output configuration. This is called SIPO method. And parallel input, serial output. This is called PISO method. Next, PIPO, parallel input, parallel output method. Here we have totally serial input, serial output, parallel output, parallel input, serial output, parallel input, parallel output. Two types of data here we are giving. At the input side, we are giving the data in the serial direction or parallel direction. At the output side, we are collecting the data in the serial direction or parallel direction. Here we have totally four different types of configuration modes for the shift registers. In this, we will start the first serial input, serial output configuration. So here the data is shifting from one direction to another direction. The data is moving in this direction. So let us see how the structure is seems to be here. Here we have totally four flip-flops. So see here, here we are discussing the 4-bit. Here we are discussing 4-bit shift register. We are discussing 4-bit shift register. Okay. So for this 4-bit shift register, we need 4 flip-flops. That means we can store here nearly 4 bits of information. So this is the first flip-flop, second flip-flop, third flip-flop, and fourth flip-flop. So these are the 4 D flip-flops are here we have. So first one, second one, third one, and fourth one. Okay. So you can represent first one, second one, and third one, and fourth one. Totally 4 shift registers here we have. Now here we have to give the data at the input side. So see here the connections are where here all the flip-flops are connected in series. So the first flip-flop output is connected to the second flip-flop input. The second flip-flop output is connected to the third flip-flop input. The third flip-flop output is connected to the fourth flip-flop input, and this is the final output. So see here the data we are giving at only one flip-flop input. Okay, so here we are giving the data at the only one flip-flop. So whatever the information you want to store in the flip-flop, you have to give the data at the first flip-flop input only. You have to collect the data, whatever the data you have stored, that data you have to collect at the last flip-flop output only. There is no other connections are available. You cannot touch this connection, this one and this one. The intermediate connection, this is called intermediate connection. Intermediate connections, that is in between two flip-flops, we have a connection. This is called intermediate. These intermediate connections you cannot touch. You can touch the input of the first flip-flop, otherwise you can touch the last flip-flop output. Okay, you can collect the data here, otherwise you can collect the data here. Alright, so this is the serial in, serial out configuration. Here you are giving the data in the serial direction and you are collecting the data at the serial direction. So here you are giving serial input data. Here you are collecting the serial output data. So now write down here serial in. Now write down here serial input. Now write down here serial output. Serial input I am giving, serial output I am giving here. And these are the D flip-flops. At the input I am giving only one bit of information at a time. So that is also called D. That is also called D. And I am collecting the output Q. And I am collecting the output Q. So see here, first flip-flop output Q, second flip-flop output Q, third flip-flop, fourth flip-flop output Qs. Okay, right. Now let us see. And coming to here, you have to connect a common clock signal, right? Now here we have to connect a common clock signal. So for all the 4 flip-flops, we have to give a common clock signal. Okay, see here I am giving the connections for the all flip-flops. So this is the clock signal. Here I have given the clock signal for first flip-flop, second flip-flop, third flip-flop, fourth flip-flop. All flip-flops are connected to a single clock signal. Okay, all the flip-flops are connected to a single clock signal. So this is the serial input, serial output configuration mode. So we are giving the data one direction and we are collecting the data another direction. So this is called serial in and this is called serial out. Just note down this figure. Okay, let us go to the next slide. Right. See here. Next, I am going to the second slide. So in this slide, we will see how the data is going to shift. So this is our 4-bit serial input, serial output shift register. This is our 4-bit serial in, serial out shift register. Now we have to see the operation here. For example, now I want to store the data 1001. Now I want to store this data 1001 in this register. Okay, right. At the end of my discussion, the 1001 data is placed here like 1001. Okay, we will take one more example. This is not good. Then we will get a clear clarity here. Okay, right. 1101 I want to store here. Okay, so at the end of our discussion, we have to store the data like this. So at the place of Q1, at the place of first flip-flop, I have to get here 1, here at the second flip-flop 1, and third flip-flop 0, and fourth flip-flop 1. So finally I have to store the data in this way, 1101. Okay, this is my aim. So my aim is I have to store the data in the 4 flip-flops in the series in the order of 1101. Now what I have to do here? Now tell me, answer. Anyone? Now I want to store the data, right? So 1101 is there. Now I can give only one bit of information at the serial input here. Okay, right. So I have 1101. In this one is LSB bit and this one is MSB bit. Okay, in this 1101, the last bit LSB bit and this is MSB bit. Now we have to give the first LSB bit at the D input. That means first you have to place one input here. You have to place here 1. Now you give the clock pulse. So previously just consider that all flip-flops has 0000 data. Now when you are giving the clock 1, this 1 is shifted from here to here. That means the output of the first flip-flop is equal to 1. The output of the first flip-flop is equal to 1 after the first clock pulse. Right? So the first LSB data is over. Next coming to that second bit is equal to 0. So when you are giving the second clock pulse, now you keep the data is equal to 0 at the first flip-flop input, and the second flip-flop input is equal to 1. Now when you are giving the next clock pulse, so this all the flip-flops are connected to the same clock pulse. When you are giving the clock pulse, all the flip-flops are going to working condition. So when you are giving the clock pulse, the one is actually when you are giving the clock pulse, the input, the second flip-flop input is equal to 1, the first flip-flop input is equal to 0. So after giving the clock pulse, this one is shifted to here. Now here the output is equal to 1, and this 0 is shifted to here. Here the output is 0. Right? So at the second clock pulse, the outputs of the first two flip-flops are 1, 0. Next, now you have to give one more clock pulse. When you are giving the one more third clock pulse, you have to put the first flip-flop input is equal to 1. Here you have to give 1. Already here we have the input is equal to 0. Here the input is equal to 1. Right? Now, when you are giving the next clock pulse, this 1 is shifted to here and 0 is shifted to here. Next one is shifted to here. Okay, let us take with some more clear example. Now I want to store the data 1101. In this, first I have to give the LSB data. So when I am giving the first clock pulse, here I am putting the data D is equal to 1. So see in the next slide it is somewhat clear. Okay, see here. Here I have 4 flip-flops. So first clock pulse, here I have given a negative edge triggered clock pulse here. This is a negative edge triggered clock pulse here. So at that time, the flip-flop is in not working condition. That means all the flip-flop outputs are 0, 0, 0, 0. So at the negative edge clock signal, all the flip-flop outputs are 0. Now coming to the first clock pulse, when you are giving the first clock pulse, here, see here. When you are giving the first clock pulse, the D flip-flop input. So see here. So when you are giving the first clock pulse, the D input is equal to 1. Okay, the D input is equal to 1, and Q1, Q2, Q3, Q4 values are 0, 0. Here it is 0. Here it is 0, 0, 0, 0, and 1. So when you are giving before the first clock pulse, before giving the first clock pulse, the flip-flop inputs are 1, and here it is 0, 0, 0, and the last flip-flop output is equal to 0. Right? Now you have given the first clock pulse. So after giving the first clock pulse, so this 1 is shifted to here, and this 0 is shifted to here, and this 0 is shifted to here, and this 0 is shifted to here. That is, the first flip-flop output is equal to 1, and the remaining flip-flop outputs are 0, 0, 0, 0. Okay, right. Now these are the inputs of the second flip-flop, third flip-flop, fourth flip-flop. 1, 0, 0. Now I am giving another input that is equal to 0. Right? Here I have used a data to store that 1001. So see here I have taken 1001 data. For first clock pulse I am giving 1, second clock pulse I am giving 0, third clock pulse I am giving 0, fourth clock pulse I am giving 1. Okay, right. Now coming to that second clock pulse, when you are going to second clock pulse, second clock pulse, the first flip-flop output is equal to Q1. So that is second flip-flop input. Now the second flip-flop input is equal to 1, and first flip-flop input is equal to 0. So this one is over. Now I have erased that and I have given 0. So after giving the second clock pulse, so this 0 is shifted to here, and this 1 is shifted to here, this 0 is shifted to here, and this 0 is shifted to here. So let us see. So here I am using for storing the data 1001. I want to store the data at 1001. I am giving this data at the first flip-flop input. Finally, I have to collect the data, same data at the output terminal, the same 1001. So 1001, I have given this data serially. Why? Because anytime I cannot give that data. So first clock pulse, before giving the first clock pulse, G is equal to 1, and remaining all the outputs of the flip-flops are 0. So this one is shifted to here. Right? So this one is shifted to here. This one is shifted to here, that is the D flip-flop input is equal to 1, then when you are giving the clock pulse, the same D flip-flop output is equal to 1, and this 0 is, the Q1 is connected to the D2 flip-flop, so the D2 flip-flop output is equal to 0, the Q2 is connected to the D flip-flop, D3 flip-flop, the output is equal to 0, that fourth output is equal to 0, so the inputs are following to the output in this way. Next, coming to that second clock pulse, when I have given the second clock pulse, at that first D flip-flop place, I have kept the value is equal to 0. I have kept the value is equal to 0. This 0 is shifted to the first flip-flop output. The second first flip-flop output previously 1, that is shifted to the second flip-flop output, and the remaining 0 is also shifted here. Next, coming to the third clock pulse. Before giving the third clock pulse, I have kept the data at the first flip-flop is equal to 0, and the previous outputs are shifting to the next stage outputs, next D flip-flop outputs, that is 00, 10. Next, at the fourth clock pulse, so this is the first clock, pulse, second clock pulse, third clock pulse, fourth clock pulse. So before giving the fourth clock pulse, at the first D flip-flop input, I have kept the value is equal to 1, and the previous outputs are 000, 1. Now, after giving the clock pulse, first flip-flop output is shifted to the second flip-flop output. Second flip-flop output is shifted to the third flip-flop output. The fourth flip-flop output shifted to the fifth flip-flop, fourth flip-flop output. Third flip-flop output shifted to the fourth flip-flop output. In this way, the output is shifted. And at the first D flip-flop, the input is equal to 1. That is shifted to the first flip-flop output. First flip-flop, second flip-flop, third flip-flop, fourth flip-flop. Four flip-flop outputs are represented here. Next. So, whatever the data you want to give, that 1001 combination you have given at the input side. So, I have given the 4 inputs for this D flip-flop. Okay, but see here, at that time, I can collect the data at the Q4 only, right? So, see here, I can collect the data at the Q4 only, but I got only the value is equal to 1. If I want the remaining data, now at the time of fourth clock pulse, all the flip-flop has the data like 1001. Here 1 is there, 0 is there, 0 is there, 1 is there. So now 4 flip-flops outputs are 1001. But my target is I have to collect the same output at the final output place, that is at the place of Q4. I have to collect the data. So at the same time I cannot collect 1001. So at the fourth clock pulse I have collected the data 1. Next, at the time of fifth clock pulse. So see here. The D flip-flop input. Actually, I don't have any inputs to give at the data side. So now I kept the D input is equal to 0 is constant. So the 0 is shifted here. The previous outputs also shifted here in this way. Okay, this 0 is shifted to here. Now at the fifth clock pulse, I got the Q5 value is equal to 0. And at the time of sixth clock pulse, the previous 0 is shifted here, the 1 is shifted here. That is, at the sixth clock pulse, the output of the Q4 is equal to 0. At the seventh clock pulse, the Q4 output is equal to 1. Why? Because the Q3 output is connected to the D4 input, so the D4 output is equal to 1. In this way, we have to give the data. In this way, we are shifting the data from one flip-flop to another flip-flop. So this is called serial in, serial out configuration. So serial in, one flip-flop input we are giving, and the same flip-flop output we are taking by using the clock signal. So whenever the clock signals you have given, at that time you will get the D flip-flop outputs, whatever it may be available at the input side. Okay. This is about serial input, serial output. So the input data for the 1001 we have collected at the output place with the help of 7 clock signals. 1, 2, 3, 4, 5, 6, 7. Totally 7 clock signals here we are using to collect the data. So this is 1001. The same 1001 data we collected at the output. Okay. So the number of clock cycles are required to get the output is equal to 7. Okay, this is about serial input, serial output configuration. Next, see here, this is a serial input parallel out configuration. That means I can give the data at the place of D only. I'm giving the input data at the place of D only. But I can collect the data at the, see here, in the how I given the input in the serial input serial output configuration. In the same way, for each clock pulse I have given the data. Now I have to collect the data like this. Parallelly I can collect. Why? Because the parallel output configuration I am discussing. That is, at the 4D flip-flops I am taking the output Q1, Q2, Q3, Q4. I am taking 4 outputs at a time. Okay, so here we have to give the input here, we have to collect the output in this way. Now, see here, you have to shift the data first. When you are in the first clock pulse, the first input is connected to the first flip-flop output. And this is the second input, second flip-flop input. Actually, the Q1 is connected to the second flip-flop input. So the Q1 follows to the Q2. So 0 is shifted to here, this 0 is shifted to here, this 0 is shifted to here. So in this way, for each clock pulse, the data is shifting. For each clock pulse, the data is shifting. So when you are giving the new clock pulse, you have to arrange your data as per your wish. So 1001 you have to give in each clock pulse. So this is the LSB bit and this is the MSB bit. See here, the first you are giving the LSB bit. From that you are giving the each bit combination up to MSB. These are the 4 bits you are giving. And at the 4th clock pulse, you got the four outputs. That is 1001 you got here. Now coming to that, the connections of the serial input and parallel output configuration. So serial input you are giving only at the first flip-flop input, and you are connecting the data 4 outputs parallelly here. So this is Q1, Q2, Q3, Q4. These are the 4 outputs you are collecting the data. Okay, right. So this is about serial input parallel output configuration, SIPO configuration. Serial input, parallel output. So serial input is there, and at the time of 4th clock pulse, I will get the data here 1001 like this. 1001, I am getting the data here in this way. Right. Next, for this for implementing this one, we need totally 4 clock signals. We require here. Next, coming to here, this is the parallel serial out configuration. In this, we have to give the data parallelly and you have to collect the data serially. So see here, for the first clock pulse at the D1, so see here, for the first clock pulse, here I am giving the data is equal to D1 is equal to 1, D2 is equal to 0, D3 is equal to 0, D4 is equal to 1. For the first clock pulse only, I am giving the data at the place of D1, D2, D3, D4. Okay. Now, after giving the first clock pulse, the outputs of these flip-flops are here. The first flip-flop output is 1, second flip-flop output is 0, and third flip-flop output is 0, and fourth flip-flop output is 1. Okay, in this configuration, I can collect the outputs at the Q4 only. I cannot take at the 4 flip-flop outputs. So, when you are going to give the second clock pulse, so close the input terminals, D1, D2, D3, D4 terminals you have to close. Now, so second clock pulse, this register working as the serial configuration. The first flip-flop output is connected to the second flip-flop input. The second flip-flop output is connected to the third flip-flop input. The third flip-flop input connected to the output is connected to the fourth flip-flop input. And this is the fourth flip-flop output. So see here, so 1001 I have given at the first clock pulse. So whenever I am giving the first clock signal, D1, D2, D3, D4, these are the 4 input signals. So 1001 I have given. At the end of the 4 clock pulses, I am collecting the data here like this. So first, after giving the first clock pulse input, the output of the Q4 is equal to 1. Okay, so at the end of the second clock signal, the output of the Q4 is equal to 0. That is, the data is shifting in this direction. Okay, this 1001 is shifting in this way. Right? So this is the total data is shifting from parallel to serial configuration. See this structure. You can understand this structure. Okay, so this is the methodology of serial input and parallel output configuration. So the total number of clock cycles are required here is 4 clock cycles. So when you are giving the 4 positive edge signals or 4 negative edge signals, this flip-flop is going to work, this register is going to work, and here we have given the positive edge triggered signals. So for that reason it is worked for the positive clock signals only. Next, coming to that, this is a parallel input, parallel output configuration, and here we are giving the data parallelly to the all flip-flops, and we are connecting the outputs parallelly from the all flip-flops. So parallel input D1, D2, D3, D4 I am giving, and I am connecting the output Q1, Q2, Q3, Q4. Okay, right. So for this, for getting the output in this parallel input, parallel output configuration, the number of clock cycles are required only 1, right? Serial input, serial output configuration. We are here the total number of clock cycles are required is equal to 7. In the serial output, parallel output, and parallel input, serial output configuration, you require the total number of clock cycles are 4. And the parallel input, parallel output configuration, you need the total number of clock cycles are 1. So in this 4 configurations, which one is very faster? Parallel input, parallel output is the very fastest configuration, but this is costly. The serial input, serial output configuration is very cheap. Compared to the pricing, the serial input, serial output is very lesser cost. It will take lesser cost, and parallel input, parallel output configuration is very cost. Why? Because this data is given by the user. So 4 input terminals you have to place, and coming to that serial input, serial output configuration, you have to give the input at only one location. You have to collect the data at only one location. But here you have to give the input at 4 locations, and you have to collect the data at 4 output locations. So for manufacturing this type of devices, it will take more cost, and it is designing of the circuit is very easy with compared to the serial input, serial output configuration, but it is very costly. Why? Because the choice, whenever the choice is given to the customer, automatically the type of components cost or circuits configuration cost is going to very high. Okay. So whenever the complete details are programmed by the manufacturer or vendor, automatically it will take very less amount of cost. Okay. Why? Because it requires extra hardware. When you are giving the total control to the customer, it will take extra hardware. When the company person is taking the decision by at the company place, it will take a very less amount of cost. Okay. So this is about parallel input, parallel output configuration. Right? Okay. Thank you.